Hello. In this video, we're going to be talking about intermolecular forces of attraction. That's what IMFA stands for, intermolecular forces of attraction, and the properties of compounds, specifically the properties of water. So our essential question for today, what properties does water have because of the hydrogen bonding between the particles? So we've already sort of looked at this question in a Nearpod, but we're going to look at it a little bit more in depth today with some simulations. So to start off, here is some data showing us the temperature at which different substances boil. That's called our boiling point. And you'll notice that there's a pattern here. These three molecules, hydrogen, water, H2O, hydrogen fluoride, and ammonia, NH3, have higher boiling points than similar compounds that have a similar molecular weight. So other compounds that are hydrides, or in other words, they have hydrogen and a group 14, 15, or 16 element. So these are all some other hydrides, and you can see their boiling points are much lower than those of water, hydrogen fluoride, and ammonia. So why is this? Well, you have to think about the force of attraction and the hydrogen bonding that's occurring in water, hydrogen fluoride, and ammonia. Remember, boiling is going from a liquid to a gas, and you need enough energy to break that intermolecular force of attraction, that attraction that holds the molecules together. The stronger the intermolecular force of attraction, the harder it is to separate those molecules. So you guys will see this in some simulations that you'll be using in this assignment, but here's an example of the first simulation that you guys will be using. If we compare a low polarity molecule, so here's a molecule that's polar, but it has a low polarity, you can see that it takes some energy to remove it. If I pull this star, that takes a little bit of energy, but it's not a lot of energy. Now let's compare that to a high polarity compound where we have lots of partial positive and negative charges. This is a molecule that's very, very polar, like water, like ammonia, and like hydrogen fluoride. Well, you can see that it takes a lot more energy to remove these molecules. It takes a lot more energy to break these bonds, to break these forces. And that's why the boiling point is so much higher, because the higher our polarity between molecules, the stronger the force of intermolecular attraction, the more energy is required to break that force of attraction. Here's another example that you guys will be using that shows the melting point. Again, here's a nonpolar substance and here's a polar substance. You guys will see this in the simulation, but I want you to make a prediction about which one you think is going to boil faster when we heat these two compounds. So when I heat these two compounds, notice here's our high polarity substance, here's our low polarity substance. As I increase the temperature, which one boils first? Well, you can see that our nonpolar substances are becoming a gas. Our polar substances still stick together. It requires more energy to break these bonds. So because hydrogen fluoride, water, and ammonia all have hydrogen bonding, which is the strongest intermolecular force of attraction, that's the reason why their boiling points are so high. This also leads to other properties that we've learned about, like surface tension. The tension of the surface of the film of a liquid caused by the attraction of particles in the surface layer. In other words, water molecules are sticking here together at the surface. And that's the reason why our water molecules bead up in this sphere, this round shape, because there's a tension. This is also the reason why insects can float on top of the water, like our water striders. Okay? This is the reason why we can fit lots of drops on a penny, and why drops are round is because of this force of attraction between the water. This hydrogen bonding leads to this property of surface tension. So if we compare a droplet of water with stronger intermolecular forces, we're going to see that water has this round shape and it sticks together. It's much more cohesive. This is our droplet of isopropanol, which is an alcohol. It's still polar, but it's less polar. It has a weaker force of attraction. So our shape is much flatter. it's spread out. It doesn't have the high surface tension that water has. Again, here's the Lewis structures for water and rubbing alcohol. You can see that water has this polarity. Alcohol is a polar group, but it also has these long carbon chains. So you can see that it's less polar than our water molecules. Capillary action is the ability of a liquid to flow in narrow spaces. So this is the reason why plants can absorb water through their roots. They're attracted to the sides of the root structure. That's called adhesion. So against the force of gravity, these water will rise up in capillary tubes. So you can see this capillary action. If we compare it to mercury, water is going to stick to the side of the tube and rise up. This also explains a phenomenon called liquid chromatography, which is the separation of a mixture based on its attractions to the solution. So in other words, if I put a dot of ink here on this chromatography paper and I put a solvent like water here at the bottom, as my solvent, my water travels up because it's attracted to the paper. The different colors in this ink are going to separate and spread, and I get this unique pattern based on which colors, which pigments have a high force of attraction and which colors don't have as high a force of attraction. So they're separated based on how attracted they are to the water as it rises up through this paper. Those with the stronger forces of attraction are going to move further on the chromatography page, and those with less strong forces are going to be separated out. Okay, so again, this just shows you the more polar substance, component B, is going to rise to the top as that solvent develops over time on this chromatography film. The less polar solvents are going to stay here at the bottom. If our solvent is polar, the more components will go higher on the paper. What do you think will happen if the solvent is nonpolar? Well, a nonpolar substance will not be attracted to the paper and it won't travel as far. So these are just some examples of properties of water and how hydrogen bonding affects these properties. Make sure you guys complete the simulation. That is the second part of this assignment.